Hey guys, we're going to be working in chapter 10 for just a couple of lessons talking about simplifying radicals. Today, lesson 10-2, I have no idea what I just wrote. Simplifying radicals. And then we'll do how to do some operations with radical expressions on Thursday. Okay, so let's talk about what do I mean by a radical expression. Remember, radical is the name for the root. So it's got to be something that deals with some square root signs or other kind of roots. Actually, we're just going to be focusing on square roots. So it's an expression that contains a radical. And so let's just review our vocab. Okay, so when we're looking at this particular radical, notice that we don't see a number here, so that means we're talking specifically about a square root. And remember that a square root is what number times itself gives you the number that's underneath this radical sign. So let me add that word, radical sign. Phrase, it's not one word. And then we've got the guy that's underneath, he's got a name, he's called a radicand, so we're going to be focusing in on him. And if I put both of these together, and I look at that radical sign with its radicand, we often just refer to this as a radical. Okay? So we're going to be focusing in on the simplest radical form. Alright, which I'm going to refer to often as SRF. Okay, simplest radical form. So I'm going to give you all the things that need to be true, and then I'm going to highlight the one we're going to be just reviewing this year, and you'll do more with this in your next math classes. Maybe not the geometry so much, but for sure the Algebra 2 trig. So this is the major thing. No radicands. So that's the value that's underneath the radical sign. Have perfect square factors other than 1. Problem is, if you have a perfect square factor of 1, square root of 1 is 1, so it really changes nothing. Okay, so that's rule number 1. Rule number 2, no radicands can have, or contain, let's contain fractions. So this is just basically saying this is not okay, but this is partially okay. And then there's a point you're going to learn, we're not going to deal with it now, is rationalizing the denominator, unless we hear something more from the high school. And then the last one is no radicals appear in the denominator of a fraction. And I can just hear you right now. Okay, Rosner, your last example then doesn't meet the rule of simplest radical form. And like I said, you're right. So only one of these is what we're focusing in on, and that's no radicands have perfect square factors. So we're going to be doing several different, in fact, we have a total of 7 review questions, or not review, but examples for your notes. So we do have a property that we are going to be following throughout our notes, and that's going to be the product property of square roots. And this fine friend says the square root of the product AB, so when I have two variables next to each other, they're being multiplied, the product AB is equal to the square root of A times the square root of B. So basically what it's talking about is we can take the square root of a product and break it down into the square root of its factors. Now, we're going to play it smart, and we're going to look for a factor that's a perfect square. If your product doesn't have a perfect square factor, then we just leave it as is. Okay? So, in other words, the square root of the product AB is equal to the square root of the factor A times the factor B. Okay, now, to be honest with you, this property also goes the other direction, and we'll see that on the last two examples. So also, we're going to say that if I have the square root of A times the square root of B, I can write that product underneath one radical sign. Okay? So we'll see that second one, the second version of the product property of square roots when we get to our last examples. So let's go ahead and get into our notes. So our directions are going to be very generic, and they're just going to say simplify, which hopefully by this point we understand that simplify means to do all the math that you can do until there's nothing left to be done. So I'm going to write a little bit of notes off to the left, and then we'll do our practice. So the first thing I want you to look for perfect square factors. Of the radicand. Now, the smallest perfect square is 1, but that doesn't change radical. It's supposed to be radicand. Sorry. So the first one you're going to look for, let me change colors so it'll stand out a little bit more. Let's do nice. There. I don't know why I always pick Christmas colors. 4. And then the next perfect square would be 9. And then the next perfect square would be 16. And then 25, and so on. So those are the guys that I'm going to be looking for to see if they're factors, okay? And then once I break it down, instead of it being a number, I now write it as the product of two factors, with one of them being a perfect square. Then I'm just going to take the square roots. Whatever I can take the square root of is going to come on the outside, and whatever I can't take the square root of is going to remain behind in a radical. Okay, so let's do a couple of examples like this. So first problem, we've got the square root of 54. So I want you to think of what is a perfect square that I can factor out of 54. And I know 9 goes in 6 times. Okay, so then we're going to take the square root of each of these. And so I get the square root of 9 is 3, but I can't take the square root of 6. And there's my answer right there, 3 square root of 6. Okay, let's try another one. 180. Okay, what's a perfect square that can go into 180? You might say, hey, you know what? It's 9. You're right. 9 can't go into that. So 9 goes into 18 twice evenly with a leftover 0. But, and I didn't really voice this very properly in the first example, because my brain's already moving, 6 doesn't have any perfect square factors. But guess what? 20 does. So I'm going to go ahead and take the square roots. I'm look for perfect square factors. So 4 is a perfect square factor. Now I'm going to color this one a little bit differently. I was a little too hasty in my other one. So I'm going to take the square root of my perfect squares. So square root of 9 is 3. Square root of 4 is 2. Now these both come outside, and because these are all factors, it all involves multiplication. Now, we had an issue with the 5. We can't take his square root. He's not a perfect square, so he gets to remain behind underneath the radical. So then my answer is 6, radical 5. All right, let's do another one of these. And we get 5. Oh, so we have a coefficient out in front. Times the square root of 24. So what are the perfect square factor of 24? Well, 4 goes in 6 times, okay? So what's going to happen in this particular case is you're going to multiply numbers, or the outside numbers multiply. Just like you saw in when I took the square root of 9 and the square root of 4, I multiplied them. Outside numbers, or outside number multiplies with an outside number. So outside can multiply with outside, inside can multiply with inside. So that's kind of how it breaks down. So again, I can take the square root of 4 is 2. Now remember, there still is a 5 outside, but now we're going to multiply by the square root of 4, which is 2. And what we have left behind is that 6. So we have square root of 6. So simplifying down further, I get 10 radical 6. Okay? Now, I'm going to complicate things a little bit, and I'm going to add a little note here. What if we have, I'll show you the example first, and then I'll write the note off to the left. What if we have a big, huge monomial that contains not just numbers, but it also contains a variable or more than one variable? So this problem, we've got the square root of 32r squared k to the 4th t to the 5th. So the deal with the exponents, they are very interesting little guys. So exponents group into even numbers. In fact, what we want to know is the highest even number that exponent can go into, okay? And then what we do is you can take the square root, of any even exponent. Okay, and the reason why we can do that is, remember that if I have the square root of x, it means the same thing as x to the half power. So what I'm going to end up doing is I'm going to be cutting in half all my even exponents. So the weird thing is I have an odd exponent, so I'll deal with t to the 5th in just a second. So let's go ahead and see if we can figure out all of our perfect squares. So I'm going to do a lot of different colors on this one. So 32, yeah, it's 4 times 8, and 8 is 4 times 2, so I get 4 and 4 is 16, so I get 16 and 2. Now, here's the beautiful thing. we've got an even exponent, so that works out well. K also has an even exponent, so I can cut him in half. But it's t to the fifth where we have a bit of an issue. So what I'm going to do is take one t out. One and only one t out. When I take 1 away from 5, that leaves me with the largest even exponent that I can get from that particular number. Okay? So now I'm just going to bring down those other two variables so they're all here as well. And now I'm just going to have a big old square root party. Okay? So I'm going to take the square root of him, and him, and him, and him, and him, and him. Now, only the perfect squares are allowed to come out. So I can take the square root of 16 is 4. Square root of r squared, half of 2 is 1, so I get an r. Square root of k to the fourth, half of 4 is 2, so I get k squared. So I take care of all of them. What's left behind? I couldn't take the square root of 2. Oops, wait a second, I forgot something. Let's try that again. I forgot to take the square root of t to the fourth. So if I take 4 and cut it in half, I'm going to get t squared. All right, now what's left behind? Let's see, we had a 2, and we have a t. So that's my answer is 4rk squared t squared, square root of 2t. Now, you could rearrange those letters to be in alpha order. It doesn't really matter. If they give them to you this way, you can give them back that way. All right, let's do one more practice like that. And we're going to take the square root of 56x, y to the 10th, z to the 5th. Now, this one is going to be interesting. So we're going to go over this. I'm going to talk about something you're going to see when you grade your homework, okay? And there's a reason behind it. So let's play the game again. So let's go ahead and see what we can get here. So 54, biggest perfect square that I can factor out of 54 is 9, and it's 9 times 6. Now, I cannot take the square root of x, so I'm just going to bring him down, and I'm just going to write x, because I really can't do anything with him. Now, the good news is the y has an even exponent, so that's pretty cool. So I will be able to take the square root of him. Now, z to the fifth has the same problem that t to the fifth had, that we're going to need to split that into a leftover z, and then that's going to give me 4. So remember, those two exponents have to add up to be 5. So here we go. We're going to have a big old square root party. We're going to do the square root of 9, square root of 6, square root of x to the 10th, square root of z to the 4th, and square root of z. So let's see what comes out. Perfect square, square root of 9 is 3. Let's see. Square root of y to the 10th. Well, half of 10 is 5. And then square root of 4 is 2, so z squared. And then left underneath the radical, oh, that's a really long radical. Let's try that again. Can't take the square root of 6. Can't take the square root of x. Can't take the square root of z. Okay, so I get 3 y to the 5th z squared times radical 6z. Oh, wait a second. I wrote down, we're good. Okay, never mind. We're fine. I wrote down a different problem in my examples. Okay, now, I'm going to tell you technically this answer is wrong. Okay? I know. How nice of me to share that with you. So technically, maybe I should learn to spell. The answer should be 3y to the 5th, but the y to the 5th needs to be in absolute value signs. And the reason for that, and let me just write it down and then we'll go back to it. I'll tell you why. So we get z squared square root of 6x z. Okay, so technically we should have radicals. So basically it boils down to this. If the variable in the radicand has an even exponent, but its square root has an odd exponent, you need to, or you should, use absolute value signs or symbols around its square root. Now, I'll be honest with you, this is not anything that we push, but you do just need to be aware of this. They may ask you about it at the high school, okay? All right, because you do have to take consideration, you don't know what that number is, right? You don't know if it's an even or if it's an odd. When you have an even, then you take the square root and you get an even. It could be even or odd, but it doesn't matter because you're going to get a positive, right? I know, complicated. All right, so let's talk about what happens when you multiply square roots. So that's our second thing we're going to do. Okay, so this is basically the process you're going to follow. You're going to multiply the coefficients. So this is like a monomial times a monomial, but they both contain radicals. Multiply the coefficients. Those are the numbers that are outside the radicals. Okay. Then you're going to go ahead and multiply the radicands. Those are the guys inside the radical or under the radical. Okay, but you're not done there because you got to double check that radicand, and if necessary, you're going to simplify it. Simplify the radicand. Can't have any perfect square factors if possible. Okay, and then we're going to do 2 quick examples and we'll be done with the notes today. So the directions do not change. Oh, by the way, this would be my second page, so I am going to I am going to retitle it Lesson 10-2, Simplifying Radicals. Okay, so simplify. Sorry about that. So we're on example 6. So radical 5 times radical 10. So basically what we're going to do, this is the opposite of the product property. It works both directions. We're going to take one radical and we're going to multiply both radicands. So this is a brain step. And we're going to get square root of 50. Then we need to see if we can find a perfect square factor. I know 25 goes into 50 twice. And then we're going to take the square root of each. Square root of 25 is 5, and I can't take the square root of 2. So that's my answer. Okay, now, this is one, I'm going to put a star next to the one I don't need. And anytime you see an equals, I should see that plus. I do want to see that part right there. Okay? And then last one, square root of 8 times square root of 6 times square root of 8. So again, here's your brain step. I'm going to multiply 6 times 8. And we're going to get the square root of 48. So mandatory to go from the original problem to the square root of 48. Then I'm going to think of perfect square factors. So, you may not see it straight away. So you might go, well, I know 4 goes in 12 times. And I know that 4 goes in 3 times. So I'm going to take the square root of all of those. And that's going to give me 2 times a radical 3, which gives me 4 radical 3. And there you go. All right, good luck with this, guys. We'll talk to you later. Bye.